should be finished with the retrograde motion worksheet. It should look something like this. If you take a look up here, you have connected all the data points, January to January. There's month 1. January is the first month. February, there's 2. So I'm going to connect the dots from January to February. From February to March, that would be 3. From March to April. And this is the direction it looks like Mercury is going with respect to the stars. But after April, when we go from April to May, it looks like it turns around and goes backwards. Does it go backwards? No. If you look, Mars, is constantly moving forward. The Earth is constantly moving forward. But here, to the stars, it looks like it's going backwards. Until we hit the 6th month, June, and then it turns around and starts heading forwards again, like this. So this, it's not actually moving backwards, it just looks like it's moving backwards. This is called retrograde motion. And the reasoning for that, the reason why we have retrograde motion is because the Earth is going around the sun faster than Mars. If you guys have ever been in a car that's on the freeway and you see a car that's way up in front of you but going slower than you, you can tell that car is moving forward. But you probably saw this as a kid. As you caught up to that car and you passed that car, you look out your window, the car, for a moment that you're passing, looks like it's going backwards. But you know it's not going backwards, it's still going forward. It just looks like, to your perspective as you pass it, that it's going backwards. And then after you pass the car, you look behind you and the car's still moving forward. It's been moving forward the whole time. Now it looks like it's moving forward again. That's what's going on with retrograde motion, is that as the car passes, or as the Earth is passing Mars in its orbit, then it looks like it's going backwards. The sun doesn't do this, because the sun, we never pass the sun. We're always fixed going around the sun. The moon doesn't do this because we don't pass the moon. The moon's going around circles of us. So we don't see retrograde motion of the sun or the moon. We only see the retrograde motions of the planets, and the planets that we're passing. Okay? And that's what Ptolemy was trying to explain. This is where we left off yesterday. Ptolemy wanted to say that the Earth was the center of the universe, but a lot of astronomers at this time, at the time of Ptolemy, were already starting to say, no, the Earth's not the center, the sun. It would make more sense if it's the sun. But Ptolemy wanted to support these ideas. And so he came up with the idea that instead of the planets, how do you explain a planet going backwards in the night sky? Well, if this is the Earth, if the Earth is the center, we have a geocentric universe. The sun doesn't do retrograde motion, just goes all the way around us. The moon doesn't do retrograde motion, it goes all the way around us, but all the other planets do. So how do you explain that? Well, Ptolemy said that the other planets did like loop-de-loops. That would make sense, because every day that planet moves a little bit further forward. If it did a loop-de-loop, it would look like it's slowing down and then going backwards. But it doesn't. They don't do loop-de-loops. The more elegant explanation is the one that Copernicus comes up with, which is the heliocentric, and I'll explain that in a moment. But here's a little video to kind of show you guys what's going on. It's basically the same thing that you guys do in the lab. By the way, the lab is due by midnight tonight. We're at the point of the year now where assignments can't be late, so make sure you hit submit by the end of the night. I will be grading these tomorrow. There's no sound of this video. It's just showing the retrograde motion. Not sure why it's not going to full screen, but what the heck? There we go. So this is just showing a graphic representation. You look at the stars in the background. Remember, those are fixed. They don't move. Just the planets, the sun, and the moon moves. That's your difference between a star and a planet. Planets in a different place every night. But you can see it looks like, with respect to the stars far in the distance, it looks like it's going backwards. And then it continues to move forward. If we were to look at it in the night sky, what you would see is every night, you see that little dot that's moving? If we took a picture of the same spot in the sky every night, that little dot would be Mars. And that would be Mars moving across the skies. Notice all the other stars don't move. Mars looks like its own little star, and it's moving like that. So it's an actual picture of taking a picture of Mars when it was in retrograde motion. This happens only about once every 2 years that happens. All right, so Ptolemy was wrong. He mathematically proved it, but we know better now. We know for sure that there's not this case of planets doing loop-de-loops. Planets don't go in loop-de-loops. That would be bad. In fact, if Jupiter did a loop-de-loop, the gravity of Jupiter would just throw every planet either into the sun or off in the outer space. So no, loop-de-loops are not a thing. Ptolemy was wrong. Even though he mathematically proved it, his math was incorrect. All right, so you guys should be back in the regular assignment now, right? You shouldn't be working on the lab anymore. If you didn't get done with that, finish that off tonight by midnight. Okay, let's get back to the lab question, or the presentation questions. Remember, question number 1 was to name the planets. The first planet was Mercury. Second planet was Venus. The third planet, or there was a television show actually named after this. Mercury was made of rock. Venus was made of rock. We're made of rock. And we're the third rock from the sun. There's a television show a long time ago called Third Rock from the Sun. I'm not going to talk too much about the Earth because, quite frankly, we live here. You guys already know. So coming up with 3 factoids about the Earth should be pretty easy. But let's just go ahead and watch the video. We got to get through the ad first, probably, right?
I have a surprise for you.
I have a surprise for you.
What? Let's say it at the same time.
Okay, 3, 2, 1.
I booked
Oh, what's the surprise? Gosh, can't even do the ads right. I don't know what is going on with the internet today, but it's not liking Google. There we go. The Earth.
The only planet known to maintain life. A product of scientific phenomenon and sheer chance. This blue speck in space holds the past, present, and future of our very existence. Approximately 4.5 billion years ago, the Earth formed from particles left over from the creation of our Sun. Gravity drew these particles together to form pebbles, which then formed boulders and eventually the Earth. At its heart is a solid inner core covered by a liquid outer core. Above this sits the mantle made of flowing silicate rocks and a rocky crust. This rocky mass is the third planet from the Sun, orbiting the star from an average distance of about 93 million miles. It's close enough to the Sun to be warm, unlike the cold gas giants, but not so close that its surface is exposed to extreme heat and solar radiation, as is the case with Mercury.
So we have actually a term for that. Astronomers have a term for that. It's kind of a funny term. It deals with a story that you guys probably grew up with as children. We call this area that we live in that's not too hot and not too cold the Goldilocks zone. Yes, from the Three Bears, Goldilocks and the Three Bears, when she's eating the porridge, one was too hot, one was too cold, and one was just right. It's an important zone because when we're looking at other stars and trying to find if maybe there's planets with other lives, we look for those planets that happen to be in that Goldilocks zone.
3. Earth's unique position in the solar system allows it to house phenomena yet to be found anywhere else in the universe, particularly liquid surface water and life. According to one theory, much of Earth's water is as old as its rocks, both of which having formed during the Earth's earliest days. Because of Earth's unique distance from the Sun, the planet is able to contain water in all of its forms, liquid, ice, and gas, rather than have them permanently frozen or evaporated into space. But Earth is the only known place in the universe with liquid water on the surface, thereby having unique cascading effects on the planet. It hydrates the land, helping create nutrient-rich soil. It collects and pools to form oceans and freshwater systems. And it cycles upward to add moisture to Earth's protective atmosphere. And where there is liquid water, there is life. About 3.8 billion years ago in Earth's oceans, primitive life existed in the form of microbial organisms. They, and the ensuing billions of years, gave rise to a range of more advanced life forms that thrived in Earth's seas, lands, and skies. As the only world known to harbor life, Earth's biodiversity is expansive in nature. An estimated 1.5 million species of plants, animals, bacteria, fungi, and others have been cataloged, with potentially millions, if not billions more, yet to be discovered. Home to life and fueled by water, Earth houses a unique global ecosystem, as curious and as grand as the astronomical events that made them possible.
All right, so that was Earth. You guys should have, what number was that? Question number, what? 11? All right, so we should be at question number 11 now, right? Okay. Maybe a name you've heard of before. This is a name that a lot of people have heard before. His name is Nikolai Copernicus. We are now getting into more modern times. Still doesn't have a telescope yet. So he's still looking with his eyes. He can still only see the sun, the moon, and the 5 planets that are visible with your eyes. But he's the guy that mathematically proves that the sun is the center of the solar system. And it goes through and explains how if we're a planet like all the other planets in the solar system, and we're going around the sun with only the moon going around us, then it explains why the planets move the way that I do. That explains why the planets move the way that they do. All right. So if you remember, Aristarchus did this a long time ago, and he had a name for this. Anybody guys remember what the name of that was when the sun's the center and all the planets go around? It was named after the god who, heliocentric, the god who would, on his chariot, he would pull the sun behind him across the sky every day. His name was Helios. In fact, it's typically what we refer to when we're talking about the sun is Helios. In fact, when we first discovered the element helium, we discovered the element helium by looking at the sun and seeing properties of a new element that we had never seen before on Earth. That's why we name it helium. Helium comes from the word Helios, which means sun. Now, if you guys get a little confused with the mythology, Helios was the Greek god who, in his chariot, dragged it across the sun. The Romans tended to steal the Greek gods and just rename them. So the Roman god who would drag the sun across the sky His name was Apollo. Okay. This is where it starts getting kind of interesting. Not a good time for religion in its history when we're talking about religion in Europe. This is that awkward conversation where I have about religion and how it's affected astronomy. And it's kind of unbelievable that this happened. So we're talking about the late 1400s, early 1500s, where Copernicus, he produces these books, these treatises, treatises of astronomy, that goes through and mathematically shows for certain the evidence behind the sun being the center of our solar system and not the Earth being the center of the universe. However, in Europe, you have to understand that this time the Catholic Church controlled everything. And when I said everything, I mean that if you had a president or a king, the King of England followed the law put down by the Vatican, by the person who was in charge of the Vatican. The most powerful person in Europe would have been the person who leads the Vatican. What's that called? You guys know what that person is? The Pope. Yeah. The Pope pretty much is in charge of everything. And what the church says during this time is law. It's probably a pretty good idea. There's some really good things that the church has given us. For example, thou shalt not kill. That's good law. All right, let's keep that law. All right, thou shalt not steal. All right, that's a good law too. 100% behind it. But remember that religion is a belief-based system, not necessarily supported by science, by evidence. So if the church says we believe something but we don't have evidence for it, by that nature, because it's so much in control, the law says that what the church believes has to be true. And the church still accepts that the earth is the center of the universe. The church says we believe that the church is the earth is the center of the universe and the universe goes around us. Which means by law, that's how it is. And if you make a book that says, nope, that's not true, that's going against the church. And that's breaking the law. And boys and girls, when the early settlers from Europe came to the United States and established our system of government, part of the reason they fought to establish our system of government was because the church's rule on the governments back in Europe. They were trying to get away from that. So our government set up, you've probably heard this before, we have a separation of church and state, which means the rules that we put down from our government are not controlled by the church, not controlled by beliefs. All right? So, this is why. People like Copernicus, who was afraid, because the church not only would go after you, they would go after your family. They would go after, if you were a teacher and you were teaching this stuff. If I was teaching you about the sun being the center of the solar system, I would be thrown in jail back then. All right? Even though I was right and I had the evidence for it. So Copernicus worried about that. He doesn't publish his treatises of astronomy until he is on his deathbed. And when I say he's on his deathbed, he doesn't have a wife, he doesn't have a kid. All of his parents and siblings have grown old and died. He's still arrested and, basically put under house arrest because he was on his deathbed anyhow. But all of the people that were part of his area of influence, they wanted him to publish these books because they're important. They give the knowledge that the world needed to know. In fact, one of his understudies, an understudy is a person who was learning along with him. You guys could almost be considered my understudies. All right? I teach you things. You guys might go out and teach that off to somebody else. Maybe one of you guys. All right. This guy named Giordano Bruno, also an Italian, takes the teachings of Nicolaus Copernicus and travels across Europe, going to institutions of learning, and teaches them how it is that the sun is the center of the solar system. And he's traveling from country to country across Europe until he gets to England. He gets to England, and the Church of England finally catches up with him, finds out what he's been telling everybody. He's labeled as a heretic. A heretic is a person that goes against church law. He's labeled a heretic. He is incarcerated. He's put into jail. He's tortured. And basically they get to the point, they call this the Spanish Inquisition. And he is told that by torture, you have to state that you were wrong. You have to make a public declaration that everything that you said about the sun being the center of the solar system instead of the earth is wrong. And he wouldn't do it. So in the end, he was literally tied to a post and burned alive. He was burned at the stake like he was a witch. So this is kind of a true story of how it was really difficult to get us to the point as a human culture to understand how things actually work. And it's one of the reasons it took us so long to get it going. When you have a belief system that denies a system of evidence, it's hard to get things done. That said, here's an idealized picture of what Copernicus maybe kind of looked like. But there's what's more importantly, his order in the solar system. The sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn. Those are the only ones that you can see with your eyes, with only the moon orbiting the Earth. Lucas. What's that? Oh, not in all actuality. I know this picture is not ideal. In all actuality, nowhere close. Like, not even remotely close. Okay. Let's just say if we were the Earth here in this classroom, the moon might be that house, across the street, for that distance. Venus would be in Bellingham. Okay, so not remotely close at all. Good question. What's this planet? Anybody recognize it? Yeah, this is Mars. How do you recognize Mars? What's the big thing that you recognize about Mars right away? It's orange. You know why it's orange? Kind of looks like rust, doesn't it? Doesn't that look like rust? Turns out it is. Mars has these massive volcanoes. It's kind of common amongst the rocky planets. We have volcanoes. These volcanoes have a lot of iron in them. The rock that's made from those volcanoes have a lot of iron in them. You put iron and you expose it to air, what happens to iron? It rusts. Wait, what in the air actually rusts? That means by looking at the surface of Mars, it must have had, either has or have had oxygen at one time because it's rusty. Now, when you look at Mars in the night sky, it doesn't look orange. With your eyes, it actually looks a little bit red. And that red told the ancient peoples, just like red is blood, red is war. So Mars is the Greek god of war. That's why we call it Mars. All right. They also have this thing that's called Men Are From Mars, Women Are From Venus. It was a popular book back in the 80s. But red was Mars. He was the god of war. Venus kind of looks bluish. And she's the goddess of beauty. And for a long, long time, the color red was associated with manliness. Men go to war. red. We wear red, right? Any variety of that color red is going to be manly. Blue is pretty and elegant and ladylike. Beautiful ladies would wear blue. That's kind of backwards from today, isn't it? Men, when you're delivered in the hospital, they put you in what color blanket? And girls, pink, which is a variety of red. So what happened? Why are suddenly we backwards from what we've been most of the time? Turns out the reason why we associate women with being the feminine color being pink and the manly color being blue has to do with an ad in New York. I think it was for Macy's. An ad that somebody screwed up and said baby clothing, the pink ones for girls, the blue ones for boys. They screwed up the colors and we've accepted it ever since. So, men, if you want to wear pink and still be manly, totally cool, because that's the color for most of the time. We've considered red and pink and all that to be manly. And women, if you want to wear blue, totally okay. Or in reality, wear whatever freaking color you want to wear because it doesn't matter. Okay. You guys notice at the top, there's a pole. Blow that up there. There's a little pole at the top there. That is an ice cap, just like we have an ice cap, but it's a little bit different. What that is, it's so cold up there, is that the carbon dioxide, which is mostly carbon dioxide on Mars, the carbon dioxide has frozen. Commonly, carbon dioxide, when we see frozen carbon dioxide here on the Earth, that's typically when we go to the grocery store and buy this special ice called dry ice. You guys heard of dry ice before? That's essentially what that is. It's frozen carbon dioxide. So what you're looking at on the surface at the planet at the top is dry ice. There's some little bit of water in there, but it's mostly carbon dioxide. Now, of course, we've been to Mars. We've sent rovers to Mars. This is what the surface looks like. It looks like a desert, and it's very rusty. But I'm going to show you guys another picture. What does this look like to you? It looks like a river, doesn't it? Yeah, if you look at it, you have this kind of meandering. In fact, you have like streams kind of feeding into other streams. It kind of branches out. There's no river there. There's no rivers on Mars. But from the first time we looked at a telescope at Mars, it looked like it had canals, which means if it has canals, it must have water. And if it has water, that means there could be life. And when we start talking about alien life, for the longest time, it was like Marvin the Martian, I'm going to destroy America. We've always looked at as Mars as possibly being the place to have life, because it's really the only place that could have water. And there's your evidence for it right there. It did, at one time, have running water. We have evidence for it. So the big question is, where did the water go? That was $1 billion question. And I say $1 billion question because we have spent billions of dollars trying to find that out. And a couple of years ago, we did. We actually found it out. One of those little rovers has been digging in the rock, and it went down a few inches, and it found the water trapped inside the ground and frozen. So there is water on Mars, and that's important because we need water. We have to have, we can't survive more than like 3 days without water. Okay? If we're ever going to leave the Earth and go somewhere else, we're going to have to go to a place that has water. All right. What question are we on number now? 14? All right. So let me play the Mars video. After this long drawn out ad from Grammarly.
To the ancient Romans, the planet Mars was symbolic of blood and war. But to many people today, the red planet may hold the key for a bright new future for humanity. The story of Mars began about 4.5 billion years ago when gas and dust swirled together to form the fourth planet from the Sun. Mars is the second smallest planet in the solar system with a diameter just shy of the width of Africa. In fact, its entire surface area is similar to that of all of Earth's continents combined. Much like its terrestrial cousin, Mars is dense and has a rocky composition. At the center of the planet is a core made of iron, nickel, and sulfur, which may have created a protective magnetic field during Mars's earlier years. Enveloping the core is a rocky mantle made of silicate minerals and a crust rich in iron. These iron minerals react with the trace amounts of oxygen in Mars's atmosphere and rusts, giving the planet its signature reddish hue. While its blood-like appearance inspired the ancient Romans to name Mars after their god of war, the planet's rusty color could be considered symbolic of the planet's prime days long past. Today, Mars is dry, desolate, and cold, with temperatures dropping as low as negative 225 degrees Fahrenheit. But billions of years ago, the planet was much warmer, more geologically active, and had a watery surface. Lake beds and river valleys snake along the face of Mars, indicating that liquid water was, for a time, present. Volcanoes, such as Olympus Mons, the largest volcano in the solar system at 3 times the height of Mount Everest, once erupted lava. But by about 50 million years ago, soon after Earth's dinosaurs died out, Mars's volcanoes also went extinct. Water on the red planet still exists today, but mostly in the form of polar ice caps. Because of factors such as the presence of water, some scientists believe life may have existed on the red planet and may exist again. Since the 1960s, space programs from around the world have launched missions to Mars in attempts to understand the planet's past, present, and potential for sustained life. Life on another planet may well be out of reach for the near future. But if any planet could give us hope, Mars may hold the key to the survival of humanity.
All right, so that's Mars. Okay, so the final story I'm going to tell today, this is going to be the final slide that I show you guys today, is these two characters right here. Tycho Brahe, and Johannes Kepler. One of my favorite stories to tell on this, because these two guys, they're the original odd couple, man. They are two very different people. Tycho Brahe, we're talking about in England about 1546, the late 1500s. Let's just say that. Okay. He is quite the character. First of all, rich. What's his claim to fame? Why is he so rich? Well, he can do something that everybody that graduates now can do, but not everybody could do back then. He can do math. He's good at doing math. He's very good at doing math. Back then, that was a rare thing. Not everybody got the education to be able to do math. And if you're a mathematician, you are not just rich, you are famous. All kinds of crazy famous. Kings and queens respected you, lords and ladies. If you had to build a bridge, you had to consult a mathematician. You had to pay this guy. If you're going to build a building, if you're going to design a city, you had to pay this guy. So this guy was very rich and very popular. And he loved to drink. And he loved to do drugs. And he had like his posse of people that kind of followed him around. This guy right here, I think if there was like a reality television show back then, probably would have been one of those. Okay? I kind of look at this guy, the party lifestyle that he has would be kind of like a rap singer today. All right? So kind of big time with that. That's kind of crazy to think somebody with an education would be overly popular, but that's him in a nutshell. So much so, if you're wondering why there's a picture of a sword fight and a nose on here, it's because, as the story goes with this guy, he one day was at he was at a party and he insulted another man's wife. In other words, he called her ugly, in a probably very, very awkward way. And the other guy challenged him to a duel of swords. And in the duel, he chopped off his nose. Now tell me if this is not the most rap star thing to do. If you get your nose chopped off, you're going to be pretty ugly, right? You can still live, but you're gonna look like Voldemort, all right? You can still have these two little nostrils. You're just not going to have a nose. So what he did was he had people make a prosthetic nose. And I'm just trying to think of like if Kanye West, if he got into a fight and got his nose chopped off and he had to have a prosthetic nose, what kind of prosthetic nose would he have on there? I'm going to guess that he would probably have a 24 karat gold nose. Could you imagine if Kanye West did that? He'd get a 24 karat gold nose. That's what he had. Apparently the noses were disattachable, and when he would do special parties, he would wear the golden schnoz at these parties. So somewhere there is a prosthetic gold nose in a museum for Tycho Rocky. Johannes Kepler, on the other hand, he is also a mathematician, but he's not as good as Tycho Brahe. He's also very interested in how the planets are moving. Now remember, we don't have telescopes yet, but he's very carefully mapping where the stars, the moon, and the sun is in the sky. In fact, he's built this giant pointer that tells you precisely what angle those are in the night sky. And he's trying to figure out how the planets are moving the way that they are, and how far away are those planets from the Earth. How did they even figure that out? But he's one of those, he's also wealthy, but he's also kind of a snob. One of those, I'm better than you type people. You should behave in a certain way, and you should not be drinking and consorting with women. So him and Tycho Brahe, they don't get along. However, Johannes Kepler really needs that information to be able to, his Tycho Brahe's math, to be able to figure out why the planets move. He can't figure it out on his own. But Tycho Brahe is kind of like, well, he's kind of like Apple. Apple's not going to share its code without paying some big money. So it's really, Tycho Brahe, he doesn't live very long. He dies at a rather early age. He dies at about my age, basically because he drinks and does drugs, and so he dies of consumption. On his deathbed, him and Johannes Kepler actually get together and come up with the laws and rules of planetary motion, which is one of the things we're supposed to be focusing on in this class, and if we have more time, we'll be doing more with it. But I can do something rather simple here, and I need a little bit of audience participation from you guys. This is where I find out who should I be passing, who I should not be passing in this class, to be honest with you. How do we know how far away, well, Venus is? You asked me about how far away Venus is a minute ago. How do we know how far Venus is? How do we know how far away as Mars is? How do we know how far away Jupiter is? Okay, we use this thing called stellar parallax. All right, so this is why I need audience participation. I need you guys right now to look at me, and I'll stand in place here. Hold your thumb out over me and put one hand over your eyes. All right, so who wants to pass this class? I see a couple people. Arm fully extended. All right, and squish me with your thumb. All right, so look at where your thumb is and where I am. Now, and cover one eye. Now, switch. Is your thumb still over me? No. You seem to have shifted, right? That's only half of it. There's a second half to this. Now what I want you to do is to hold your thumb about halfway. Now cover your eyes, put your thumb over me, and then switch. Did your thumb move the same distance? It moved further, didn't it? This is called stellar parallax. In fact, this is called stereoscopic imaging. It's the process that they use when they make 3D movies. They use two cameras that are just slightly off from each other. And then you put on these glasses, the glasses are polarized to where you're seeing one image from one side and another image from another side. And that's what gives you that 3D perspective. The reason you have two eyes and those are facing forward is to let you know how far away something is. Your brain is processing that automatically. I have this poster. I don't know if you guys have ever seen this poster back here. It's kind of sort of hidden. These were really popular back in the, I want to say late 80s, early 90s. Have you guys ever seen one of these? These are called magic eye posters. It doesn't look like anything. But if you look at this and you focus your eyes, your focal points right here, this image is actually two images superimposed on each other. It actually is a 3D image. There's some dinosaurs and some trees. If you want to try this out, I'll have this up somewhere in the classroom, but you guys can try that out later. I can help you. But that's like a 3D image of those things. All right. So what does this have to do with planets and stars? Well, if we have, let's say, an asteroid, and it's probably moving towards the Earth, we probably want to know how far away that asteroid is, right? So here's the Earth, and we look at the stars. Those are stars, not just squiggles, all right? We look at the stars beyond that asteroid. On this side of the Earth, we'll have some sort of telescope, and it takes a picture of this asteroid, and it'll be next to those stars right there. Over on this side of the Earth, at the same time, this picture, telescope is going to take a picture of the asteroid, and you'll notice to their perspective, it's going to be behind that star. Well, there's a fairly simple formula, and this is going to be the next lab that you guys are working on. There's a fairly simple formula that we can figure this out using trigonometry, a little geometry. If we could figure out the distance from here to right between these 2 points, that distance right there, and we can see what this angle is right here, then we can figure out the distance from here to here. All right? And we call that the stellar parallax. So, what's going to happen next is, that's the last slide from today. Yes, we're going to continue on with this astronomy beginnings listening assignment. It's going to take us a couple more days to get through. But what I want you guys to do right now is to open up right here where it says stellar parallax of stars. It should look something like, should look like this. And you should have blue writing in there. Anybody that opened up the lab right after I made it, you might not have the blue writing. You need to reopen the assignment. I had to delete that assignment and do it again. So this is going to be what we're going to work on for the remainder of this class and a good chunk of next class. It's fairly simple. You are going to need to read this part because I haven't told you everything, so reading is important. And then here are the instructions, and basically with the instructions, you and a partner, so you're going to have to get a partner, you may move around to get a partner, are going to hold a ruler like this, and your partner is going to hold it for you, and you're going to hold this up, and you're going to cover one eye, and you're going to look and see where that pencil is, and you're going to cover it, and then you're going to move it to a different place, and you're going to do basically what you guys were doing a minute ago, and answer a few questions. You guys are going to get up to question number 5, and I'm going to stop you guys from working, and then we'll work on past that. But that is where I'm going to stop for now. I'm going to stop the video. Goodbye, people in video.